Justin Miller, Upstart College Physics here. We've got some enlightening information to go through today. So let us just begin, right? We've been talking about charges, charge-charge interactions, and ultimately we want to talk about what does the force due to when we have two charges? And you say, well, it's due to the charges themselves, right? Yeah, but it's not due to contact between the charges. And how do we explain forces that don't require contact? That's right, we explain them with some sort of field theory. So this is where we want to start to identify the field which mediates the force between charged particles. So we want to start talking about what's known as electric fields. Electric fields, and we're going to stick with due to point charges. All right, so again, we have force at a distance when we have 2 point charges, but what if we just have one, right? Take a singular isolated point charge. And I'm going to call it capital Q just to say, hey, it's some big charge. And we can take it, it's a point charge, sure, but I'm just going to draw it like this. And I'm going to make it positive and say this is our point charge Q. And we ask ourselves, is there anything in particular that connects with this charge, that has to do with this charge? And you say, well, I don't see anything, I just see the charge there. And I agree with you, that's all I see. I see the charge. That's it. But then we ask ourselves, well, what happens if another point charge just pops into the picture? Instantaneously, we'll say. So we'll say that we've got some little q, we'll make it plus. Say that this pops into existence, defying the laws of physics, if you will. But we're just doing a hypothetical here. It pops into existence. What happens regarding that charge? Well, all of a sudden there's a force on it, right? There's a force of interaction due to this charge and this charge now. So we're just going to consider this little charge here. And it pops into existence, and there is now force exerted on it due to big Q. What direction is that force? And what's the magnitude of that force for that matter? Well, we know some things, right? If this charge happens to be a radial distance away, which we could call R, then the force of interaction lies along that, or aligned with that line connecting the two. And we say, well, they're both positive charges, so this would be a repulsive force, and ultimately the force of interaction would be out this way. And we'll just call that F sub Q, the force on charge Q. There we go. Well, just as well, if that charge were to pop in, say, over here, the force would be down that way. Charge were to pop in over here, the force would be down that way. Charge over here, force that way. This charge could have popped in anywhere. And the direction of the force would have been, or is, radially outward with respect to this charge here. So I don't want to make it seem like I'm popping in a bunch of charges, but we'll say that the charge could have been over here, or here, or here, or here. And with respect to the force exerted on these charges due to this, we'd have this force would be out this way, this force would be out this way, this force would be down this way, this force would be out this way, and so on. So what can we conclude from that? Well, again, we've got force at a distance here. And we explained that through field, through a field, in this case, an electric field. So what we can say is that this charge itself produces an electric field in its vicinity. And it is that electric field that interacts with any other charges that are in its vicinity and mediates the force. All right. Let us go ahead and say that, then, shall we? We can say that the charge Q produces an electric field in its vicinity that is responsible for exerting a force on any other charges in its vicinity. Let us say that the force that it exerts is equal to, the charge that it's interacting with multiplied by the electric field that that charge produces. Let's say the force that Q exerts on another charge is given by F is equal to QE. We're going to say hat. This is the force on the little q and the electric field due to big Q. So let us write this. F hat is the force exerted on Q. Q is the charge under consideration. With respect to the force. And E hat is the electric field vector produced by the charge Q at the location of little q. Whew. Kind of a mouthful there, but that's what we got going on. So let's say that that's the case. That would seem to be reasonable, that it's the electric field of the charge, big Q, that interacts with this little q, and that produces the force on that charge, little q. So let us see what we can do with this. Well, we've already noted that that little q there in the vicinity of BQ, the force on it would be radially outward, considering that they're both positive charges, right? So what if we just went ahead and said that the electric field due to big Q is radially outward? Because this and this have to be aligned. They're the only vectors there. Q, that's just the charge, which can be positive or negative. But again, we're considering a positive charge here. So let us note that force on any charge plus Q in the vicinity I'm forgetting the end there. The force on any charge plus Q in the vicinity of big Q is radially outward with respect to big Q. So then the electric field. And this is how I write electric field a lot. E hat, it implies that it's a field, but E hat field. So what if we went like this, and we just said, okay, here's our big Q right here. It's positive, here's our big Q, and we can imagine that surrounding this charge is an electric field. An electric field that points radially outward. So, that one looks a little bit off there, huh? Yep. The big Q. So it's got this electric field, right? And if we stick another charge into it, that electric field interacts with that charge and exerts a force on it. If it's a positive charge, the force is in the same direction as the field, radially outward. We'll get to negative charge here in a second. But this is how we can sort of identify the field itself. But we should also note that the force of interaction depends not just on the location, it depends on how far away, which does have to do with the location, but it's not just the angle that it makes, it's the magnitude as well that has to be considered. And we already know that the magnitude of the force of interaction between two charged particles is inversely proportional to their distance squared. So how can we put all this together? Well, let us go like this. We've got that the magnitude of F hat would be equal to the absolute value of Q times the magnitude of E hat. Just talking about magnitudes here. The reason we take the absolute value is so that we're, again, just utilizing magnitudes overall, positive. And if we talk about this, well, what is the magnitude of the force for point charges? For 2 point charges, we've got the magnitude of the force of interaction between them is equal to K sub E, absolute value of Q1, absolute value of Q2, divided by R squared. And this is just Coulomb's law, right? The magnitude of the force of interaction between two charged particles, Q1 and Q2. Well, what happens if we go ahead and say, let's let Q2, or really Q1, doesn't matter, be the big Q. Q2 be this little q that we put in this picture here, which I can go ahead and draw one in my eye. In this little q here. What do we get then out of this? Well, all that we've done is we've taken this to be equal to big Q, this to be equal to little q, and we can write this out. Then we have that the magnitude of the force is equal to K sub E, absolute value of big Q, absolute value of little q, divided by R squared, where R is the distance that they're separated by. Right there. Well, why do we want to do this? Because we can factor this little q out, right? Factor it out. And I'm going to write it right here, right next to this one. And write again, the magnitude of F hat is equal then to, I'm going to take this little q out front and write little q multiplied by K sub E, absolute value of big Q, divided by R squared. Get that out of the way a little bit. And then what do we do? Compare these two. The absolute value of Q times this quantity, or the absolute value of Q multiplied by the magnitude of the electric field. What does that tell us? If we're dealing with point charges, the magnitude of the electric field due to this big Q is this right here. This is the magnitude of the electric field, K sub EQ over R squared. The magnitude of the electric field dies off is 1 over R squared. It is proportional to the charge under consideration producing that electric field. So that's the conclusion here. We conclude that the magnitude of the electric field due to Q is given by magnitude magnitude of E hat from Q is equal to K sub E, absolute value of dq, divided by r squared, where r is the distance you are away from that charge, Q is the charge, and K sub E is Coulomb's constant. So now we can draw kind of a bigger, clearer picture of the electric field due to this point charge, big Q. And that is that it is radially outward and that its magnitude decreases as we get further and further away. Thus, so does the force it exerts on any charge placed at a given location. So, we can take some positive charge here, we can draw the electric field. The electric field gets weaker and weaker as we get further and further away. So the electric field right here, here's the electric field vector. Radially outward, in this case would be the I hat direction. Here, we're further away, we're still along, say, the x-axis. It's weaker, but it's still I hat. Get further away, it's still weaker, but it's still I hat. Over here, it does the same thing. It diminishes in strength. And I'm just drawing in a few of the vectors associated with this electric field. Really, it fills up all space in its local vicinity. Everywhere there is a defined electric field that has a magnitude and a direction. I go and say, well, what about the electric field right here? Well, it's radially outward, and it has a certain magnitude based upon how far we are away from the charge under consideration and the magnitude of that charge itself. So, this is what we get. The electric field due to a point charge is given by K sub E Q over R squared. There's no need to have the big Q anymore. That was just saying, hey, we got this really big charge. That's for any charge. And notice here that I'm not taking the absolute value of it. There's a reason for that that we'll get to right here. K sub E, Coulomb's constant, Q is the charge reducing the electric field under consideration. Sorry. R is the radial distance away from Q. And we've got ourselves K sub E, of course, Coulomb's constant. Then we've got this R hat. R hat is a unit vector in the radial direction. R hat is just radially, well, positive R hat's radially outward, and negative R hat's radially inward. That is such that a positive Q gives us a radially outward electric field, and a negative Q, the negative again, goes directionally and would give us negative R hat, radially inward. So, plus Q, minus Q. And then we've got this. The electric field due to any given point charge can be gotten through that expression there, at any point in space. positive point charge. We've got this. Getting messy here, but really messy. A little too fast, but that's okay. We get the picture. Radially outward depends on where you are in terms of what the magnitude and the direction is. So in this case, we would have that the electric field at this point right here would be like that. It would have a magnitude which would be dependent on the radial distance away from this charge here, which we'll call charge Q. And say that E hat would be equal to K sub E, Q divided by R squared, R hat. So it depends on both the magnitude, how much charge we have here, and how far away we are from the charge, and then the direction is completely determined geometrically by the vicinity in which we're trying to determine what the electric field is. We come over here, the electric field's that way. We come over here, the electric field's that way. And that's all, again, geometrically determined. So that would be for a positive point charge. And then if we take ourselves an isolated negative point charge, some minus Q here, and because Q would be negative, we have it's in the negative R hat direction, which means radially inward. So for the negative point charge, we get something like this for the electric field. And so on, all over in space. Radially inward towards it. It's the same expression though. This is the expression. I want to know what the electric field is right here. We're some radial distance away from the charge, R, and we have the direction of said electric field would be radially inward, pointing back towards it. It would have some magnitude based upon how far we are away from this charge, and the charge itself, how much charge we've got there, and that's it. So if we have an isolated point charge, we've got radially outward, K sub E Q over R squared, R hat for positive, and radially inward, K sub E Q R over R squared, R hat for negative. That's it. Pretty cool, huh? So this is how we're going to be treating things. Now notice something. We'll take these both to be isolated and say that over here, I go ahead and say, you know what? I'm going to put another plus charge here. And I'll call this like some Q2. Say, well, what's the force on Q2? Well, the force on Q2 is going to be radially outward because it's another positive charge. And that's the same direction that the electric field would be at that location. They're aligned with one another because the force on a positive charge in an electric field is in the same direction as the electric field. Always again, right? F hat is equal to Q E hat. Q is positive, F and E hat are in the same direction. On the other hand, if we say, no, you know what, there's a negative Q3 here, we'll say that this one goes away. So we're only looking at two charges. Well, in this case, we still have that the electric field is radially outward, but the force is now radially inward. Oops. That looks ugly. Force on that charge because it's attracted to this one. So again, we still roll with this right here. F is equal to Q E hat. A Q can be positive or negative, which means that the force can be in the same direction or in the opposite direction as the electric field. Positive, same direction. Q's negative, opposite directions. And that's how we conventionally identify things. I stick in a negative charge here. Well, what do we have? We've got that the electric field here is radially inward, right? Due to this charge, and we have that the force exerted on this charge would be in the opposite direction of the electric field, because again, it's a negative charge. And we get a repulsive pair here. On the other hand, if we go ahead and say, you know what, there's a positive charge over here, a lone positive charge, what do we have? Well, we have again that the electric field is in this direction, and we also have that the force exerted on this charge would be in the same direction as the electric field because it's a positive charge. It's attracted to this charge. So that's what we've got. We don't need two charges to look at the electric field. All we need is one. We say, what's the electric field look like due to this charge? We can draw this all out. Now, commonly what you'll find is people utilize what's known as electric field lines that give you what the contour of the electric field looks like locally. And sometimes they're a little bit easier just to draw out, but it's typically easier than drawing a bunch of little vectors everywhere in space. And I can just say, hey, electric field lines are often used in drawing. Contours of the electric field due to some charge configuration or distribution. The lines are like tangent at all points to the direction of the electric field. Tangent to the electric field. At all points in space. And the number of lines per unit area or volume signify the strength of the electric field. Signify strength, which is the magnitude. More lines, greater strength. Less lines, less strength. This should be like more lines per area in 2 dimensions. So let's just draw out the electric field lines for a point charge configuration, singular point charge, and just get that. So we can take some positive Q here, and we want to draw out the electric field lines. Well, they're tangent to the direction of the electric field at all points, and the electric field is just radially outward, so the lines themselves just go like this. And they're all over in space, truth. But what do you know? When we're close to the charge, there's more lines per unit area. As we get further and further away from the charge, there's less lines per unit area. The line density decreases as we get further away. And that signifies that the strength is weaker, or the magnitude is less as we get further away. So it's a way, again, to visualize electric fields rather than drawing a bunch of little arrows all over the place, which gets daunting at times. But that's it. We'll utilize it from time to time, but that is it. The electric field due to point charges, case of EQ over R squared, R hat. We'll be using it a lot, and we'll be building on it. All right, that's it for now. Until next.